Space is vast, but our question tonight is simple. Could humans really survive on Mars? The red planet is cold, dry, and thin-aired, yet it's also the most Earth-like destination we can reach, with frozen water, useful minerals, and days not so different from our own. Why go at all? Because long-term threats from climate shifts to stray asteroids remind us that a second home could be a lifeboat for civilization. Around the world, space agencies and private teams are sketching real plans. Safer rockets, smarter landings, habitats that shield us from radiation and turn Martian soil and sunlight into food, fuel, and air. If this journey sparks your curiosity, tap like and subscribe to keep exploring with us. Ready? Let's set course for Mars. In the summer of 1969, a human footprint pressed into the moon's dust and changed what felt possible. The first steps happened far from home, yet they made Earth feel bigger, as if the sky had unfolded a new page. That moment still guides how we think about the next frontier. Many signs suggest the next historic footprint will not fall on grey lunar soil, but into the red grit of Mars. The question is no longer only about reaching it. The question is whether people can live there, work there, and call it home. The distance between an idea and reality has shrunk. In the 1960 seconds, engineers were inventing almost everything from scratch to reach the moon. Today, we inherit decades of flight data, new materials, reliable rockets, and a better map of space. The tools are stronger, the math is tested, and the road is partly paved. Sending people to Mars remains hard, but we are closer to that goal than the Apollo generation was to its first moon landing. The arc of progress bends toward Mars because knowledge compounds. Living on another world would be one of the greatest tests our species has ever faced. It asks us to build a small, complete version of civilization where none exists. Air, water, shelter, food, medicine, power, and trust would have to travel with us or be made there. The timeline would be measured in years, not days. Every system must run safely, not just during landing, but through dust storms, long winters, and the ordinary wear that comes with daily life. There is also a quieter reason driving this effort. Our planet is generous, but it is not guaranteed. Climate patterns are shifting. Seas rise and storms grow stronger. Forests burn, and heat presses into places it did not before. None of this means Earth will suddenly fail, yet it reminds us that a single home is a single point of failure. History holds other warnings. Large asteroids have struck Earth in the deep past with world-changing force. Another strike of that scale is unlikely in our lifetimes, but not impossible in the long run. Planning a second home is insurance for a species that thinks in centuries. A settlement away from Earth would not replace our duty to care for this planet. It would add a layer of safety, like a lifeboat you hope to never use. It would also change what we can do. A community beyond Earth could test cleaner industries, try closed-loop farming at scale, and learn to recycle nearly everything. Lessons could flow back home to help heal the biosphere that raised us. The act of building such a place may become a tool for fixing the one we already have. Mars draws attention because one fact stands above many others: water. Over years of missions, spacecraft found water ice at the poles, tucked under soil, and locked inside minerals. Water means oxygen to breathe and hydrogen for fuel if we break it apart. It means steam to drive machines and liquid for growing plants in sealed habitats. Where water can be found or created, lasting life support becomes more than theory. That simple molecule changes Mars from a distant idea into a practical target. Agencies and companies have moved from talk to design. NASA and the European Space Agency plan missions that map landing sites, test entry and descent systems, and push rovers to explore ancient riverbeds and lake floors. Private groups, including SpaceX, work on heavy-lift rockets and reusable stages, aiming to lower cost and increase flight frequency. The plan is not a single leap, but a staircase. Robots first, then cargo landers, then crew, then habitats that expand piece by piece. Each step learns from the last. Distance sets the first challenge. A trip to Mars takes about 6 to 9 months with current technology. For that long, crews will live in microgravity, which means near weightlessness. Bones thin without regular stress, muscles weaken, body fluids shift toward the head and can affect vision. The fix is steady exercise and better spacecraft design, maybe even rotating sections that create a gentle, artificial gravity. These are engineering problems with known tools, but they demand discipline and space to train. Radiation is the second challenge. Beyond Earth's magnetic field, high-energy particles from the Sun and from deep space can pass through the body and damage cells. This kind of energy, called ionizing radiation, can change DNA and raise cancer risk. On Mars, the atmosphere is thin and the planet has no strong magnetic shield, so the surface is also exposed. Habitats will need shielding. We can use layered materials, tanks of water that double as protection, or even walls built from local soil. The safest work may be done underground, carved into rock, or covered by regolith to block the constant particle rain. Even getting down to the surface is a puzzle. Mars's air is too thin for parachutes alone to slow a very heavy craft, yet too thick to ignore. Landers must combine heat shields, parachutes, and powered descent with precise timing. The process has to work the first time, and then again and again. Because cargo and people will arrive in waves, the more mass we land softly, the more tools and shelters we can bring, and the sooner a settlement can stabilize. The planet itself is not kind to exposed skin. The pressure at the surface is less than 1% of Earth's. Without a suit, the low pressure would let moisture at the body's surface turn to gas. Saliva and tears would start to boil away. Air is mostly carbon dioxide, which we cannot breathe. Temperature swings are wide. Dust is fine, clings to surfaces, and can carry electric charge. None of this is a reason to give up. It is a checklist for design. Strong suits, clean airlocks, careful filters, and smart materials can turn a harsh place into a livable one. Because the challenge is so large, some call it unprecedented, and they are right. A permanent settlement requires closed loops, plants or bioreactors to turn carbon dioxide into oxygen, machines to reclaim water from breath, sweat, and waste, systems that repair themselves or can be fixed with printers and spare parts made on site, food grown under lights, in soil mixed from local rock and compost, or in vertical trays that sip water and recycle nutrients, power from sunlight, and, later, small reactors that provide a steady base. Everything must be simple to operate, but robust enough to run for years. The dream of living on another world did not start yesterday. It followed the first satellites, then the first people in orbit, then the moon landings. Book by book and mission by mission, the idea grew. Among all the worlds our probes have visited, Mars stands out. It is not gentle, but it is not impossible. Day length is close to Earth's. Gravity is lower yet not zero, which can help with construction and heavy lifts. Seasons change. Skies hold clouds. Ice sits at the poles. These echoes of home matter. They help people picture life there in more than outlines. When cameras first flew by Mars in the 1,960 seconds, they sent back a raw, red desert. Later orbits revealed canyons longer than any on Earth, volcanoes vast enough to stretch the horizon, dunes that drift, and dry channels that look like riverbeds. Polar caps come and go with the seasons. Wisps of clouds cross the sky. If you squint at some landscapes, they look like parts of Arizona or Australia, except the colors lean toward rust. Each familiar feature shrinks the mental distance. It tells us this is a world with rules we can learn. These clues fueled a steady campaign of exploration. In 1996, NASA launched the Mars Global Surveyor and set a tone that lasted. Build a program, not one mission. Orbiters map the surface and the weather. Landers test the ground. Rovers carry labs on wheels and drive into the field. The plan is simple. Gather enough science to understand the planet's story and find the safest, most useful places for future crews. Over time, the program has moved through clear phases. The first phase carried a straightforward idea: follow the water. On Earth, liquid water and life travel together. Instead of chasing life directly, which is hard and easy to get wrong, scientists searched for water's signs, minerals that trap it, shapes in the land that flow with it, ice that melts and refreezes. From the early 2000s through about the next decade, mission after mission found evidence that Mars once held lakes, deltas, and groundwater. They found clays and salts that form in wet conditions. These discoveries turned maybe into very likely for past water. As confidence grew, the focus widened. In 2011, the Curiosity rover arrived with tools that could drill into rock, sniff the air, and scan for complex carbon molecules. Scientists call these molecules organics. They do not prove life by themselves, but they are the building blocks for cells and chemistry. Curiosity's job was to ask whether its landing site had what life would need: water, a stable environment, and the right chemistry. The answer leaned toward yes in the distant past, which encouraged the next step. The second phase looks for signs of life more directly. European missions under the ExoMars banner planned to drill deeper than before, down where radiation has not broken molecules apart. NASA's Mars 2020 mission, which delivered the Perseverance rover, began to collect and cache samples in a place that once was a lake with a river delta. Deltas on Earth trap and protect delicate layers of mud and organic matter. The idea is to find rocks that might carry textures or chemicals shaped by ancient microbes, then seal those samples for a future trip back to Earth's best labs. The third phase is about people. Designing for crews has already begun. Engineers study how dust behaves on solar panels, how to pull water from ice or hydrated minerals, and how to make methane and oxygen for fuel from the carbon dioxide in the air. Habitat concepts look like linked cylinders or partially buried domes, with thick walls for radiation protection and internal farms for food and air refresh. Timelines shift as budgets and technology change, yet many planners point to the late 2030 seconds as a window when the first crewed mission could be ready. When it happens, it will mark a new kind of milestone, like the moon landing did for its time, but aimed not at a flag and a footprint at the first building blocks of a town. These steps trace more than a plan. They echo something old in human nature. People move toward open edges. They cross mountains, oceans, and deserts, not only for trade or safety, but because curiosity is a deep engine. That same engine can guide us into space. Colonizing, in this context, does not mean repeating the harms of history. It means building humane, careful places that respect both worlds, Earth and the one we enter. It means carrying responsibility along with ambition. If we do it well, the benefits multiply. A city that must recycle almost everything becomes a perfect teacher. Waste turns into resource. Energy systems learn to be steady and clean. Farming methods adapt to tight spaces and low water use. Medicine learns to work with fewer supplies and more prevention. These are not only Martian skills, they are Earth skills, made sharper by necessity and sent back across the gap. There is also the long view. A species with 2 homes is harder to wipe out than a species with 1. That matters in a universe where rare events still happen across long time scales. Space can hold the materials to grow without cutting deeper into Earth's living systems. Metals in asteroids, ice in shadowed craters, sunlight spread across deserts and orbit. If we can learn to build in a way that keeps nature whole, our numbers can grow while our footprint on Earth shrinks. This path is not about escape. It is about resilience. It is also about access. A base on Mars would be more than a shelter. It would be a port for science, a factory for fuel, a workshop for new machines, and a school for skills we have not yet named. With each shipment and harvest, it would rely less on Earth. With each year, it would teach us new habits of careful living. The first crews would be pioneers, but the goal is normal life. Meals at a table, repairs done on a schedule, and laughter in a place that once was silent. Mars looks like the best place to try first, yet it is not the only place. The Moon is close, which makes it a practical starting point. Lunar ice can be turned into water and fuel. A linked set of habitats on the Moon could test systems and train crews for Mars. Asteroids, too, hold value. Small companies and teams imagine harvesting water and metals from them and refining propellant in orbit, turning rocks into gas stations and machine shops. Each target plays a role in a larger network that pushes human presence outward. Every piece of this plan rests on careful science. That is why the Mars exploration program builds momentum in phases. It asks a sequence of clear questions. Where is the water? What chemistry exists? Are there signs of past life? And what places are best for people to land and live? Robots answer what they can. People will answer the rest. Not because humans are better than machines, but because hands and minds on the ground can try more ideas, fix more problems, and notice more small things that matter. We should name the risks plainly. Rockets can fail. Landers can miss their mark. A habitat can spring a leak, or a dust storm can darken the sky for weeks. A machine that keeps water pure can break. A person can get sick far from a hospital. These are reasons to slow down, not to stop. Redundancy, training and design reduce risk. Communities on Earth run with the same logic. Fire stations, spare parts, backup power, and neighbors who check on each other. A Martian town would do the same, by rule and by culture. Cost is part of the story. Launching mass is expensive. Time is expensive. People's lives are priceless. Reusability brings the price down. Making fuel off-world brings it down further. Shared standards, open data, and international cooperation turn multiple small gains into one large effect. The lunar neighborhood can become a place where agencies and companies test the hard parts before pushing to Mars. Each success pulls the future a little closer. For all the planning, we should keep our expectations steady. A first mission will not look like a city. It will look like a field camp. A cluster of pressurized rooms, cables running between them, a greenhouse full of leafy greens, a workshop packed with tools organized by need, a rover parked under a shade. People will wake, check systems, repair, explore, eat, talk to family over a long delay link, and sleep. The days will be busy and sometimes dull, which is a sign of safety. After a few rotations of crews, the temporary will become permanent, almost by accident. Children may one day be born under a sky the color of butterscotch. They will learn the constellations differently, and they will learn Earth as a place across the dark, as real as a parent's voice and as distant as a childhood story. Their schools will teach both worlds. Their holidays will mark new seasons, tied to the tilt and orbit of a world that turns more slowly and takes longer to circle the Sunday. They will inherit rules written to keep life precious in a place that gives nothing away for free. Science will keep leading the way. The follow-the-water era taught us that Mars once had the right conditions for life as we know it. The search for organics and subtle patterns in rock layers now pushes us toward an answer to a deeper question. Did life begin twice in one solar system? If even tiny fossil clues exist, they will change how we think about life across the galaxy. If they do not, that answer matters too. It will mean that life needs more than water and time, and we will keep learning what that more is. Meanwhile, the engineering keeps folding back into daily use. Radiation shielding that is light and strong. Software that watches systems and flags problems before they spread. Farming methods that harvest water from air and nutrients from waste. Medical kits that do more with fewer supplies. Batteries and reactors that carry a settlement through long nights. Each improvement is a tool that helps both planets. None of this implies that Mars is easy. It is not, but it is tractable. That is the right word for a problem we can break into parts, test, and solve. We have done this before, in other forms, with vaccines, bridges, power grids, and global networks. The key is patience, clarity, and steady hands. The goal is to build a place where ordinary life can unfold under an unfamiliar sky. We are unlikely to see a single flag moment that declares the job done. We will see launches that become routine, cargo that lands quietly, and updates that sound simple. A new greenhouse module attached, a water well tapped a little deeper, a lab upgraded, a child's drawing sent with a data packet back to Earth. Taken together, these will be the signs that a settlement has crossed from fragile to durable. Mars is the best target today because it offers enough of what we need and asks enough of what makes us better. It asks for teamwork across nations. It asks for engineers who listen to scientists and scientists who listen to builders. It asks for planners who think in decades and citizens who support careful, open progress. It asks for humility and care because a misstep can cost a life and because both planets deserve respect. The Moon, asteroids, and Mars form a ladder. The first rungs are in reach. Step by step, we can build a network of places that support each other. Propellant made from ice, metals shaped into structures, farms grown under glass, labs that read rock histories like books. With each rung, we gain experience and lower risk. With each rung, we give future generations more choices. In time, the memory of the first footprint on Mars will join the Moon's dust in our shared story. People will remember the date and the words spoken, but they will value most the quiet work that followed. Valves turned, seeds planted, panels cleaned, books read aloud in a habitat at dusk. Such details are the true marks of settlement. They show that life has learned to fold itself into a new place without breaking. The line that began with a boot print on the Moon continues toward a home on Mars, not a replica of Earth, but a careful extension of it. Not an escape, but a promise kept that we will use knowledge to make life more secure, more creative, and more durable wherever we are. Step by step, system by system, season by season. This is how a world becomes livable. But the reason we focus this monumental effort on Mars rather than the Moon or other options comes down to a simple ledger of physical advantages and resources. Mars holds several quiet advantages when the goal is not a quick visit, but a place that can stand on its own. Yet these advantages come with severe survival challenges that must be mastered. It is larger than the Moon, with more space to build and more raw material to use. It has minerals, buried ice, and a thin blanket of air that, while not breathable, can be turned into resources. The Moon, by contrast, is smaller and has a hard vacuum at the surface. A world with even a fragile atmosphere gives engineers more options. It means you can slow a spacecraft with air, as well as rockets, shield habitats a little better from micrometeoroids, and harvest gases for fuel and farming. For a self-sustaining town, these details matter. They turn a harsh outpost into a place that can grow. The Martian air is mostly carbon dioxide, about 96%, with a pinch of argon and a little nitrogen. None of that is safe to breathe, yet it is useful. In a sealed greenhouse, simply compressing the outside air raises the pressure to a level where plants can live, while filters and added oxygen keep the mix right. Carbon dioxide, or CO2, is plant food. Nitrogen supports plant growth and helps build proteins. Argon can be used for certain industrial tasks. Mars also stores water as ice and as permafrost, the name for frozen ground that stays solid year after year. With water and CO2, you can split molecules and make oxygen for air, hydrogen for fuel, and, through simple chemistry, methane and oxygen propellant. The Moon has pockets of ice in deep shadow, but it lacks an atmosphere and the broader spread of accessible volatiles. For closing life support loops, Mars begins with more of the pieces we need. When we line Mars up next to Earth, the likeness is not perfect, but it is closer than any other planet or moon gives us. Temperatures on the surface can rise to around 20 degrees Celsius at the equator on clear days. Nights drop far below freezing, yet heat is a problem we know how to solve, with suits, insulation, and steady power. Air pressure is low, less than 1% of Earth's at sea level, but it exists, which matters for engineering. The land carries familiar shapes: plains, dunes, mountains, and canyons. These are not for comfort. They are for planning. They show that wind and weather work there in patterns we can study and predict. Gravity shapes health. On the Moon, surface gravity is about 1/6 of Earth's. On Mars, it is about 1/3. Years on the International Space Station have shown that long stretches without gravity weaken bones, thin muscles, and change how fluids move through the body. Exercise helps, but it is not a full cure. A pull of 1/3 is still less than home, and we do not yet know the long-term medical effects, but it is closer to what our bodies expect than the Moon offers. For building, moving equipment, and growing up children, that extra pull may be important. The length of a day matters more than it first appears. A Martian day a Sol lasts about 24.5 hours, almost the same rhythm as our own internal clocks. People can wake, work, eat, and sleep on a schedule that feels natural. Machines can run cycles that match life. Compare this to the Moon, where a single day lasts about 28 Earth days from sunrise to sunrise. There, you face 2 weeks of bright sun, followed by 2 weeks of deep cold and darkness. Energy storage and thermal control become enormous tasks. Mars sits about half again as far from the sun as Earth, so sunlight is weaker, but it is steady enough for solar power and farming under glass when the air is clear. These practical similarities explain why plans have moved from paper to hardware. NASA's long-running work, often grouped under the banner Journey to Mars, has flown orbiters, landers, and rovers that map resources and test ideas. Private companies, including SpaceX, aim at the same horizon and design heavy-lift rockets, Starship-class vehicles, and cargo systems meant to lower the cost of sending mass to deep space. The shared mindset is gradual and methodical. Early crews do not settle a city. They assemble greenhouses, test water extraction, and confirm that air and power systems perform as designed. Later crews expand farms, add new modules, and replace imported goods with local production. Food is a good example. At first, everything edible arrives from Earth. Then a mission grows leafy greens and herbs for freshness and morale. With time and practice, diets shift toward crops raised on Mars. Only after many cycles could a base trust itself to live mostly on what it produces. Building such a place will take years, and every year demands technology that behaves like a patient partner. Mars may look familiar, but it is still hostile. The air is thin enough that, without a suit, bodily fluids at the surface would start to boil, not because they are hot, but because the pressure is too low to keep them liquid. In seconds, a person would lose consciousness from depressurization. Even if pressure were not a problem, the mix of gases outside has almost no oxygen. .2 cannot support human breathing. Without added oxygen, the brain runs out of air in minutes. Then there is the dust. Martian dust is fine, sharp, and charged. It scratches seals and joints, finds its way into every gap, and can carry chemicals that are hard on lungs and electronics. In a few weeks, constant exposure without protection could be dangerous to health and ruin gear. These facts do not end the plan, they shape it. Habitats must be pressurized and leak tight. Airlocks need careful design, with dust traps and surfaces that can be cleaned easily. Filters and masks become everyday tools. Suits must be strong, flexible, and comfortable for long shifts, with reliable heat and pressure control. Inside the base, air has to cycle through scrubbers that remove CO2 and add oxygen. Water must be captured from breath, clothing, and waste, then cleaned and used again. Growing food means carefully managing light, water, and nutrients in controlled spaces that keep pests and microbes in balance. Power systems must handle routine loads and also ride through storms and night with room to spare. Because the environment is hard, some have proposed changing the environment itself. The word for that is terraforming, using planetary engineering to alter a world so it becomes more Earth-like. The goals often start with a thicker atmosphere and a warmer climate. Over very long periods, the target shifts to a mix of gases that includes oxygen in amounts people and animals can breathe without tanks. This is not a short-term fix. It is a concept measured in centuries and more, and it would be expensive. Still, it is worth understanding, because the steps reflect how climate works and how linked the pieces are. Right now, Mars is cold and dry, and the air is very thin. Those three traits reinforce each other. When a planet is cold, water locks into ice, often mixed with soil, and stays trapped. Thin air cannot hold much heat, so temperatures fall fast after sunset. With little water vapor or other greenhouse gases, heat slides back into space. The trick in many models is to start a warming loop and let physics do part of the work. If the surface warms a bit, some of the buried CO2 and water can turn into gas and drift into the air. That thickens the atmosphere. A thicker atmosphere holds more heat and keeps nights from getting as cold. Warmer ground then frees more gas, and the loop continues. Several strategies have been explored on paper. One is to place large mirrors in space and aim sunlight onto the surface. Concentrated light would warm targeted regions, especially near the poles where water, ice, and CO2 frost sit ready to evaporate. Another is to add strong greenhouse gases that trap heat more effectively than CO2 does. Fluorocarbons, man-made compounds used in some refrigerators and industrial systems, can act this way. They are far more powerful per molecule at stopping heat from escaping to space. On Earth, we work to reduce such gases because they overheat the climate and can harm the ozone layer. On Mars, used carefully and in the right forms, they could be a starter for a warming cycle. In both ideas, the intent is to push the average temperature up by a modest amount at first. In some simulations, an initial increase of about 10 degrees Celsius can unlock large stores of CO2 from soil and ice, which then adds more greenhouse warming and shifts the total rise much higher, perhaps 5 times that first step. If such a feedback were reached and held, surface temperatures could climb to ranges that feel familiar at least part of the year. Ice bound in the top layers of soil would melt. Liquid water would flow in lowlands and collect in ponds and shallow lakes, though winds and dust would still mark the climate as Martian, not terrestrial. With more air above, pressure would rise. Moving from a deadly thin atmosphere to one that can help support the body is a big gain, even if the air remains unbreathable without adding oxygen. Over very long spans, biology could help adjust chemistry. Plants and microbes turn CO2 into oxygen, given light and nutrients. But the scale is vast. Making a whole planet oxygen-rich takes more time than a human career. It fits into the language of many centuries, not decades. These ideas are not fantasy. They come from climate models and ecological theory. Yet, every part of them demands machines that mine, refine, and manufacture in bulk on another world, plus careful control to avoid accidents. Mirrors the size of cities must be built, launched, and positioned. Factories must produce greenhouse gases and release them without harming early settlers. Monitoring systems must track the air and the ground. The price in energy and money would be high. The time would stretch beyond many lifetimes. While such a plan might suit a long view of civilization, it does not help the first people to land or the first base to survive its first winter. For that reason, planning returns to the present tense. The near-term work is to master living on Mars as it is. Crews will rely on pressurized habitats for air and warmth, not on a changed planet. They will mine ice with drills and heaters and store water in tanks inside thick walls where radiation cannot reach it. They will make oxygen from CO2 and water with solid tested equipment. They will wear suits anytime they step outside and check seals before they do. Greenhouses will stay sealed and clean, with pressure and humidity kept steady. Dust will be a constant chore. At the door, air showers and sticky mats will pull grains off fabric and boots. Rovers will park in covered bays. Filters will be replaced on a schedule that people will respect almost as ritual. The case for Mars remains strong even with these limits. A world with air, ice, and a day that matches our own gives our species a real shot at a self-supporting foothold. The program logic runs through stages that make sense. Scout and measure, land and test, build and grow. Along that path, space agencies keep collecting data under a steady plan, while private groups design systems to deliver mass again and again. The two approaches, public and private, match well when the goal is a stable ladder instead of a single jump. Compared to the Moon, the difference in gravity and day length alone changes how a base would feel. People can keep a normal workday. Farm lights can match a sunrise and sunset that arrive about when bodies expect them. Waste heat from machines can keep greenhouses warm at night. Solar arrays can feed batteries that last until morning, with less storage than a 2-week lunar night would require. Reactor options add reliability. Over time, the base would trade weak links for strong ones, from imported air to local production, from fragile suits to improved materials, from dusty halls to cleaner workflows. Each swap lowers risk. Even with all this progress, the core dangers remain plain. Without pressure, a human body fails in moments. Without oxygen, a human brain fails in minutes. With dust in the lungs and gritty particles in joints and seals, life grows harder with each week outside. These truths do not call for fear, they call for respect. They also call for design that expects mistakes and forgives them. Double gaskets, valves that close by spring if power fails, habitats that can be isolated if one is compromised, training that turns emergency steps into calm habit. Culture shapes safety as much as hardware does. If we imagine the first decade of regular missions, a pattern appears. The earliest crews prove that greenhouses can support steady harvests of simple crops, leafy greens, hardy root vegetables, beans, and grains bred or selected for low light, low water, controlled environments. Later, groups diversify diets and experiment with fruiting plants and small amounts of animal protein produced with care for water use and waste. At each step, food stays a supplement until results are dull and reliable. Only then can shipments from Earth lighten, and even then, contingency stores stay full. Fuel follows a similar path. CO2 from the air and water from the ground can be turned into methane and oxygen. With enough production, return vehicles can carry less fuel from Earth and refill on Mars. That change lowers costs and opens room for more cargo. The same plants that turn CO2 into oxygen also clean air and water. Bioreactors extend the process with fast, controlled cycles. Nothing leaves the loop unless it must. In a small ecosystem, waste is not a burden. It is a feedstock. Settlers will learn this lesson well and live by it daily. As the base grows, shelters will get thicker and smarter. Passive shielding, piling local soil over roofs, blocks radiation without constant energy use. Windows become small, layered viewports, or they become screens fed by exterior cameras that show the landscape without letting dust inside. Vehicles stay simple and tough. Software watches for leaks, odd power draws, and temperature shifts that hint at trouble. When alarms sound, they do so gently and specifically, teaching crews to trust them instead of ignore them. Debate about terraforming will continue in parallel. Some will argue for early steps, small mirrors to warm landing zones, pilot projects that release limited greenhouse gases to test models, and controlled plantings of hardy microbes inside sealed plots to study how they process CO2 and make soil. Others will caution against pushing a whole planet before we understand every effect. Both views can be held with care and patience. The first duty, after all, is to the people living there and to the planet we are using. The second duty is to knowledge itself. For planning, it helps to keep timelines clear. A thicker and warmer atmosphere might be reachable with heavy industry and careful control. A breathable atmosphere with oxygen at Earth-like levels is far beyond any near-term project. People will need suits and habitats for a very long time. Settlements will adapt to that reality. Streets may be tunnels, plazas may be pressurized halls with trees and water recycled through fountains, and outside will be a place you visit with discipline, like a workshop filled with powerful tools. Life will be normal inside and technical at the door. The reason to accept these limits is simple. The benefits are large and compounding. A base that runs on almost closed loops becomes a lab for sustainable living. Every gram of water learns a job it will do again. Every watt of power is counted, saved, and used wisely. Crops teach resilience, and people learn to fix before they replace. Back on Earth, cities can borrow these methods. Factories can cut waste with the same care that keeps a greenhouse green. Homes can reuse water and heat with the same logic that keeps a habitat safe at night. In the end, Mars does not promise ease. It promises a fair test. It offers enough familiar traits: air to compress, ice to melt, days that match our clocks, gravity that pulls us down to let us try. It demands enough of our best traits: patience, accuracy, cooperation, to make us better if we succeed. The Moon will help as a training ground and as a neighbor for early industry. Asteroids will help as waypoints and sources of metals and volatiles. But for a place to plant long roots beyond Earth, Mars holds the most cards in our favor. Terraforming can wait its turn in a long story. For now, the task is simpler and more urgent. Learn the land well. Build machines that do what they are told every day without drama. Keep people warm, fed, and calm. Harvest water and turn air into something life can use. Grow food until you trust the taste of it. Clean the dust off the door and the panels. Watch the sky for weather and the horizon for change. A base that does these things month after month takes its first real step toward becoming a town. Across all of this, the order of work stays constant. Use what the planet gives: CO2, nitrogen, argon, sunlight, and ice. Add what we must bring: knowledge, discipline, spare parts, and time. Accept the parts we cannot change soon: thin air outside, toxic dust, and the need for walls between us and the cold. Respect the scale of ideas like mirrors in orbit and greenhouse gases made on another world. Name their costs, weigh their risks, keep them as options for a future that has earned them through steady success. Mars is not a mirror of Earth, but it is a world where a human home is possible with care. It sits at a balance point, challenging, yet generous enough to reward good planning. That is why it draws engineers and explorers, why programs grow around it, and why rockets are being built with it in mind. Its surface lets us imagine streets, farms, labs, and classrooms under bright lamps, all linked by pressure doors and common purpose. Its sky, thin and salmon-colored, will hang above those halls as a reminder that life there is chosen and made, not given. If not, a careful, pressurized civilization can still thrive, using the very skills that keep astronauts alive in orbit today, scaled up, layered, and humanized. Mars offers more of what we need than the Moon does, and it keeps time in a way our bodies understand. But before we can begin, we must first master the greatest unseen threat to human biology: the constant, high-energy particle rain of space. Radiation sits near the top of the challenge list because it is both invisible and relentless. High-energy particles move through space like tiny bullets. They strike cells and can break strands of DNA, the long molecules that carry instructions for life. Earth softens this constant rain with a thick atmosphere and a global magnetic field that steers many charged particles away. Mars has neither in strength. Its air is thin, and it lacks a planet-wide magnetosphere. As a result, the surface receives far more radiation than people are used to on Earth. From time to time, the Sun also throws storms called solar proton events. During these bursts, particle levels spike, and the dose rises quickly. Spacecraft have measured what this means in practice. The Mars Odyssey mission found that radiation levels in orbit around Mars are roughly 2.5 times higher than what astronauts see at the International Space Station. If a crew were exposed to that level for about 3 years, the total dose would approach NASA's current safety limits. That is close enough to force careful design. The risk is not only long-term cancer. Radiation can also damage blood-forming tissues, raise the chance of cataracts, and chip away at the immune system. Studies suggest that protons from cosmic rays may cause more serious DNA breaks than earlier models predicted, which pushes mission planners to add more protection. Protection starts with simple physics. More mass between people and space. Thick walls help. Tanks of water stored in the right places double as shielding. Materials rich in hydrogen, like certain plastics, can blunt some high-energy particles better than metals. Underground spaces or habitats covered by Martian soil, called regolith, block even more. Storm shelters inside the base give crews a place to wait out solar flares, where extra shielding stacks around a small room to push the dose lower during short spikes. NASA and its partners also study active systems such as plasma deflector shields, which would shape electric or magnetic fields around a spacecraft. These ideas are promising on paper, and lab tests continue, but no method is yet 100% effective for all types of radiation across long missions. Until that day, the plan layers partial solutions: smart routes and timing, passive shielding, strong procedures, and real-time monitoring. Radiation is not the only hard truth. The other major wall is cost. Launching mass out of Earth's gravity well is expensive, and deep space missions multiply that expense with life support, redundancy, and time. If we used the budgets and methods of the Apollo era as a guide and scaled them forward to Mars, some estimates place the effective cost at around $10 billion for each person delivered. Numbers like that make a self-sustaining settlement impossible. A town cannot grow if every new resident costs the price of a major airport. To build a permanent base, the cost per person and per kilogram must fall by orders of magnitude. Lowering cost is not a single trick. It is a set of linked changes. SpaceX has focused on that set with a clear goal: make long-range spaceflight cheap enough to scale. The first key is full reusability. Most rockets in history fly once. Imagine air travel if every airplane were thrown away after a single trip. The ticket for even a short flight would be out of reach. Rockets must learn to act more like planes: launched, landed, checked, and launched again. The second key is refueling in orbit. If ships can reach low Earth orbit mostly empty and then top off their tanks from tankers, they can leave Earth lighter and cheaper, yet still have the propellant they need for the push to Mars. The third key is making propellant on Mars. If return vehicles can refill there, they do not need to carry all their fuel from Earth, which saves huge mass and cost. The fourth key is choosing the right propellant for that plan. Methane and oxygen, for example, can be made from carbon dioxide in the air and water in the ground using known chemistry. This combination also stores well and burns clean. None of these steps alone is enough, but together they change the math. As reusability improves and refueling works in practice, the price per trip can drop sharply, opening room for cargo that builds real infrastructure instead of single-use stunts. Even with cheaper launches, getting people and heavy equipment safely down to the Martian surface remains a knot that must be untied. Landing on Mars is not like landing on the Moon, and it is not like landing on Earth. The air at Mars is too thin to slow a massive vehicle with wings or parachutes alone, but it is thick enough to heat a vehicle fiercely during entry and to push it around with winds and shock effects. The sequence today looks like this. A heat shield and aeroshell absorb the first blast of energy and slow the craft from orbital speeds to supersonic speeds. A supersonic parachute then opens to cut the speed further. Finally, rocket engines fire to guide the last stretch and set the vehicle down softly. This stack of methods has worked for small robotic landers and rovers. The largest payload we have delivered so far is about a metric ton. For human missions, the target payload is an order of magnitude larger, at least 10 tons, and more safely 20 to 30 tons in a single landing. The gap between 1 ton and 30 tons is not a matter of simply scaling up a parachute. To bridge that gap, engineers are testing new ways to slow down and control heavy craft. Supersonic retropropulsion, where engines fire while the vehicle still moves faster than the speed of sound, is one path. Inflatable or deployable decelerators that increase drag without extreme mass are another. Better heat shields and guidance systems improve accuracy so that cargo and crew can land near each other and join up without long drives across rough ground. Each technique must handle a planet that never behaves exactly the same way twice. Dust changes air density, seasons shift winds, local terrain shapes turbulence. The margin for error is thin, and the system must work on the first attempt with people on board. Because of this, landing technology is a top priority inside NASA's long-term plan for Mars. The agency's work under the Journey to Mars umbrella continues to test entry, descent, and landing methods so that a crewed vehicle in the 2030 seconds can trust each step from space to surface. Radiation, cost, and landing meet at one more point: scale. A base that depends on a constant stream of expensive freight is brittle. A base that can land heavy equipment safely can install better shielding, larger farms, and more reliable power. A base that can make its own fuel can support rescue and return options without long delays. This is why reducing launch prices, refueling in orbit, producing propellant on Mars, and building robust landing systems are not separate projects. Together they create a supply chain that can grow. The radiation problem keeps shaping daily life even after landing. Crews plan surface work to match forecast conditions. When the sun is quiet, tasks outside last longer. When space weather warns of a flare, people move inside the storm shelter and shift to indoor maintenance, analysis, and training. Dosimeters, small badges that measure radiation dose, become as normal as a watch. Data flows back to doctors and engineers on Earth to refine models and personalize protection. Over months and years, habitats gain layers and smart layout. Sleeping areas deep inside, storage tanks in the outer rings, control rooms near the center. Windows are small and set behind thick panes. Views come mostly from cameras and screens, which show the landscape without letting radiation and dust inside. The cost problem, meanwhile, turns into a design constraint that encourages simplicity. Systems share parts. Pumps, valves, and electronics follow common standards so that a single shelf of spares can fix many failures. Tools fit many tasks. When something breaks, crews do not ship it home. They mend it or melt it down and print a new piece. This mindset, driven by budget and distance, is also a safety mindset. Fewer unique parts mean fewer single points of failure. Reuse at the system level mirrors reusability at the rocket level. The same logic that lands a booster to fly again also builds a greenhouse rack that can be reconfigured instead of replaced. Landing innovation shows up in base layout as well. If heavy cargo can be set down with accuracy and gentleness, delicate equipment arrives in better shape. Large prefabricated modules can land intact. Power systems can be assembled from fewer, bigger pieces, which simplifies maintenance. Precision also lets planners choose landing zones with both safety and resources in mind. Firm ground, gentle slopes, and access to buried ice. The early years will likely see a cluster of landing pads that expand into a small port. Dust control becomes part of the design pads with hardened surfaces, berms to catch debris, and washdown or air knife systems at airlocks to keep regolith outside where it belongs. As for propulsion choices, the link back to cost appears again. Methane and oxygen engines promise clean burns and good performance. If methane and oxygen can be made on Mars at scale, return flights can be planned with fewer unknowns. Propellant plants will sit near power hubs, turning electricity, water, and carbon dioxide into fuel and oxidizer. Tanks will fill slowly but steadily between launch windows. When a vehicle arrives, it can top off for the trip home or for a hop to another site. This gas station model is simple to picture and powerful in effect because it turns Mars from a one-way destination into a node in a growing network. None of this erases the reality that radiation is a health risk that cannot be fully removed. Even with thick walls and careful timing, crews will take on some extra dose by choosing to live and work on Mars. That choice must be informed and voluntary. Medical screening, ongoing health checks, and honest communication about risk will be part of the culture. At the same time, technology will keep pushing the dose down. Better materials, smarter storm warnings, and possibly active shielding will cut exposure year by year. The goal is simple. Keep each person's lifetime dose within safe bounds while still doing meaningful work. The money story will also remain in motion as more rockets land and fly again, as orbital refueling becomes routine, and as factories on Mars begin to produce fuel and common materials. Costs should fall. They fall not just because each flight is cheaper, but because each kilogram landed does more. A single machine that can print parts, process soil, or build panels replaces many discrete shipments. A local supply of propellant and water turns each mission into a multiplier for the next one. Private companies will push for efficiency. Public agencies will push for safety and reliability. Together, they will turn rare missions into regular logistics. Landing systems will keep improving through practice and data. Each successful descent teaches engineers about shock, heating, and control at Mars. Sensors watch how parachutes behave, how flames interact with thin air, and how dust clouds rise and fall around thrusters. Software learns from small errors and trims paths on the next try. Over time, vehicles will move from proof of concept to workhorse. The measure of success will not be one perfect landing, but a long series of safe, boring ones that deliver what they promise. When we put these threads together, a picture forms. First, protect people from radiation with a layered approach that uses mass, smart layout, and active monitoring, while research tries to add new tools like plasma shields in the future. Second, crush the price curve through full reusability, refueling in orbit, and propellant made on Mars, paired with propellant choices that fit local chemistry. Third, master entry, descent, and landing for heavy payloads by combining heat shields, parachutes, and powered descent with new methods designed for thin air. Fourth, scale payloads from the 1-ton class to the 10 to 30-ton class so that we can land habitats, power systems, farms, and factories intact. These are not 4 separate missions. They are one system that lets people not only touch Mars, but stay. The timeline that carries this system forward matches the broader plan already in motion. NASA's work toward the 2030 seconds aims to retire key risks for a first crewed mission. Private advances aim to make each step affordable. The 2 paths meet on the surface, where a base that can shield its people, feed itself more and more each year, and refuel its ships can turn the red planet from a destination into a second address. Step by careful step. The problems that feel absolute radiation, cost, landing become engineering tasks with checklists and spare parts. That is how exploration grows into settlement, not with one grand gesture, but with many well-made decisions that hold up under real sky. Choosing where to place the first base is not just a map exercise, it decides how people will live each day. NASA has been building a short list by weighing 2 needs at once. The site must carry high scientific value, so that every hour on the ground returns knowledge about how Mars formed and whether it ever hosted life. It must also offer the resources that let a crew survive without a constant stream of supplies from Earth. Water sits at the center of that plan. On Mars, it can be drawn from 3 main sources: ground ice buried under soil, water vapor in the thin air, and hydrated minerals, rocks that hold water within their crystal structure. Oxygen is the other pillar. Mars provides a path here, too. Its atmosphere is mostly carbon dioxide, and with the right equipment, carbon dioxide can be split to release oxygen for breathing and for fuel. With those basics in mind, the debate turns to latitude. The polar regions look attractive at first glance because their ice is not subtle. It lies in large, rich sheets. A drill can reach it quickly. Ice can be melted for drinking, turned into oxygen and hydrogen, and used to grow plants. The problem is light. At the poles, day and night come in long blocks. Darkness can last for almost half a Martian year, which is close to an Earth year. 2 things follow from that. Solar power becomes difficult, since panels would need to store vast amounts of energy or sit idle. Temperatures plunge for long stretches, raising the load on heating systems and stressing batteries. None of this makes the poles impossible, but it pushes them down the list for the first base if the main power source is the Sunday. The equator offers the opposite experience. It is the warmest band on Mars and changes the least with the seasons. Day and night arrive with a steady rhythm, close to the 24.5-hour Martian day that fits human clocks. For solar power, this regularity is a gift. Panels can run a reliable daily cycle, and greenhouses can match the light to healthier plant growth. The trade-off is water. Near the equator, shallow ice is rarer. Crews would need to rely more on pulling water from hydrated minerals or from the atmosphere, which is possible, but slower and more energy-hungry. Equatorial sites also sit under some of the planet's largest dust storms. These storms can reduce sunlight for weeks, and any solar-heavy base would need strong energy storage and careful planning to ride them out. Between these extremes lie the mid-latitudes, and many planners see them as a practical compromise. At these middle bands, you can find places that receive at least some sunlight all year, avoiding the months-long polar night while still staying cooler than the equator. Importantly, radar and surface data point to buried deposits of water ice that are shallow enough to reach with reasonable drilling rigs. They are not the huge fields found near the poles, but they are accessible and widespread. Mid-latitude temperatures remain harsh by Earth standards, Yet they bounce within ranges that life support systems can handle without heroic measures. For a first base, the balance of steady light and reachable ice is hard to ignore. Within these bands, specific sites matter. Terrain sets the difficulty of landing and the danger of dust devils. Local weather shapes how panels perform and how often suits must be cleaned. Elevation changes the thickness of air overhead, which affects entry and descent. Communication lines run through the sky. A location with a clear, frequent line of sight to Earth or to relay satellites simplifies daily operations. Engineers read these factors together and look for stability more than spectacle. One proposed location that often enters the conversation is nicknamed Noctis Landing. It sits at the western end of Valles Marineris, the giant canyon that cuts across Mars. The site rests near the canyon floor, but within a broad, open stretch where landers could set down and crews could build without tight walls around them. Supporters like that, the sky there stays wide enough to see Earth rising above the horizon on a regular schedule, which helps keep communication strong without relying solely on a dense satellite network from day one. The canyon itself tells a deep story about water, lava, and time. Layers of rock, there are like pages in a book, stacked one on another, waiting for tools to read them. For a first base, that means a short walk to science targets and a short drive back to shelter. There is also a case for stepping stones that do not touch the surface at all. The small moons Phobos and Deimos circle Mars close in. Both are tiny compared to our moon. Phobos is only a few tens of kilometers across, Deimos even smaller. Their gravity wells are so shallow that landing and launching require far less energy than a surface mission. They always keep the same face toward Mars, like our moon does toward Earth. From the Mars-facing side of Deimos, a crew could operate robots on the planet below with a delay that is barely noticeable on the order of 1/10 of a second for the signal to go down and back. That makes telerobotics feel natural. A person can drive a rover, dig, and handle delicate tasks in near real time. These moons could act as safe pit stops, places to test, long-duration life support, stage fuel, assemble cargo, and learn how people cope with deep space living while keeping the risk of heavy landings off the table for the earliest missions. Using the moons first would not end the need for a base on the ground. It would buy time and data. Crews could scout multiple landing sites by proxy, watch dust patterns change with the seasons, practice sample handling, and qualify entry, descent, and landing systems without people on board. Phobos or Deimos could also host communications arrays and fuel depots that later surface missions would use. From there, hops into Mars orbit and back become routine, and the final drop to the surface happens with more confidence and more support. Once a site on Mars is selected, the next decision is how to build a home that stands up to the environment. Astronauts who step onto the surface will likely stay for months at a time, tied to launch windows that come only every 2 years or so. They will face big daily swings in temperature, a thin atmosphere that cannot hold heat, and radiation that leaks through the sky even on calm days. A safe habitat must absorb all of that without failing. It must stay pressurized, warm, and clean. It must block radiation and keep dust outside. It must be simple to operate when crews are tired and complex enough to handle emergencies when things go wrong. NASA's work has explored several construction paths with these needs in mind. One of the most striking concepts is the Mars Ice Dome. The basic idea is elegant. An inflatable structure, light enough to ship from Earth, is set up by robots before a crew arrives. Pipes and pumps then fill the space around it with water drawn from local ice. In the cold Martian air, That water freezes into a thick shell of ice that hugs the inflatable core. The result is a dome with a clear job. Use water itself as the shield against radiation. Ice is rich in hydrogen, and hydrogen is good at slowing and absorbing the high-energy particles that come from space. Because many regions of Mars hold water just below the surface, the raw material for this shell does not need to be imported. The planet supplies its own armor. The ice dome's form brings other benefits. Ice can transmit light. With careful control of thickness and surface coatings, the dome can let in a soft, even glow during the day. That light can guide plant growth and help people keep a healthy day-night rhythm. Views of the outside world become possible without large, heavy windows. Seeing the landscape matters in ways that are easy to forget on Earth. It ties people to the place they live and lets them track weather and dust by eye, all while staying behind a protective shell. The build sequence aims to be simple. Robots deliver and anchor the inflatable frame. A small crew of machines drills for ice, melts it, and pumps water into the outer layer. As the shell thickens and hardens, it gains strength. Once a safe thickness is reached, the interior can be pressurized and warmed for human use. Because most of the mass, the water, comes from Mars, the shipment from Earth stays light. Modules for sleeping, labs, and storage fit inside. If more space is needed later, another dome can be added and linked by pressurized corridors. Comparing this approach to burying habitats highlights the trade-offs. Digging and covering structures with soil works well for radiation protection, but it demands heavy excavation equipment, strong vehicles, and a lot of energy. Those machines are bulky to ship and hard to repair in the first years. The ice dome avoids large earth moving by switching the shielding material from soil to frozen water. It lets crews build protection without cutting or lifting tons of regolith. Above-ground structures also make maintenance easier. Crews can inspect the outer surface, patch cracks, and add layers as needed without tunneling. If a leak appears, it can be found and fixed with direct access. Keeping the dome stable is a matter of thermal design and pressure balance. Inside, the air must be warm enough for people and plants. Outside, the ice must stay cold enough to remain solid. The solution is to separate the two with liners and insulation. Reflective films can limit heat flow into the shell. A thin gap of cold air, or even vacuum, between inner walls and outer ice can cut heat transfer further. On the outside, coatings can slow sublimation, the process where ice turns directly into vapor in thin air. If small gaps appear after micrometeoroid hits or surface wear, they can be sealed with melted water that refreezes into the shell. In this way, water becomes both structure and repair material. Radiation protection improves with thickness. Water tanks can be built into the top of the dome to add more shielding where it matters most. Sleeping areas can sit closer to the center where the most mass surrounds them. A compact storm shelter can be placed in the deepest part of the habitat with extra layers of water and supplies around it, ready for solar events. These design choices mirror what crews already do in orbit, but scaled for a fixed address. Light inside a dome is not only for comfort. Plants use it to turn carbon dioxide into oxygen and food. A well-lit greenhouse, attached to or nested inside the dome, can serve 3 roles at once: food production, air recycling, and water cycling. Condensed moisture can be captured and reused. Nutrients can move in tight loops through soil substitutes or hydroponic trays. A small ecosystem grows that buffers the base against short supply gaps and adds fresh variety to meals. Location, resources, and habitat type are linked. A site rich in shallow ice pushes the ice dome toward the front of the line. A site with less water but steady sunlight might favor habitats built from shipped modules with added shielding from tanks and panels. In all cases, pressure, heat, and dust control sit at the core. Airlocks must handle frequent use without leaking. Floors and tools need surfaces that shed dust or trap it where it can be cleaned away. Filters have to be replaced on a schedule that becomes part of the base's rhythm, like taking out the trash on Earth, only more important. Communication sits quietly over all of this. Bases near the equator, or mid-latitudes, have reliable lines to Earth for part of the day, but not always. Relay satellites in Mars orbit will knit the gaps. Until that network is thick, sites like Noctis Landing that keep Earth in view more often will feel easier to run. The moons, again, can help. A small array set on Deimos could relay signals for both hemispheres and watch weather patterns unfold, warning bases of storms before the sky above them turns dark. Power will likely mix sources. Solar arrays work well where light is steady and dust can be managed by design. Raised panels, smooth surfaces, and low-friction brushes or gentle air jets. Small nuclear reactors, if approved and available, would add a constant baseload and carry the settlement through storms and nights without strain. Ice domes and other habitats can be wired with redundancy, so that a single failure does not darken an entire block of rooms. Over time, the first base will teach the limits of each choice. If mid-latitudes prove ideal, future sites may dot the same band, each close to local ice. If canyon floors like Noctis Landing deliver a good mix of science and operations, more crews will follow the terrain into similar valleys. If the moons as pit stops show their worth, logistics chains will grow from Earth to Deimos to Mars and back, with fuel and parts flowing like a slow, steady river through space. What matters now is that site selection and habitat design work together from the start. The question is not only where is the ice, or how do we shield from radiation? It is where can we do both with the least risk and the most learning? A base is successful when daily life becomes predictable. That means water that arrives when it should, oxygen that stays at the right levels, lights that rise and dim on a schedule, and doors that seal every time. The Mars ice dome is one promising way to wrap those needs into a single, buildable shape. The mid-latitudes offer a landscape where sunlight and shallow ice overlap. The moons offer a gentler first step that builds the skills and hardware to make the surface effort safe and sustainable. As planning continues, the map will fill with candidate ellipses for landing and circles for keep-out zones, with marks for drill sites and greenhouse pads. Each mark represents a choice guided by simple rules. Stay within reach of water, keep the sky in view, protect against radiation, let people work in shirt sleeves inside a strong shell. The tools to follow those rules are getting clearer. Whether the first base rises under a canyon's open sky or begins its story from the Mars-facing slopes of Deimos, the path forward ties the planet's gifts, ice, carbon dioxide, and light to designs that make those gifts usable every hour of every day. A safe habitat is only the shell. To live day after day in a place as harsh as Mars, people will need a full toolkit of machines and systems that keep life running. Some serve directly clean air to breathe, clean water to drink, steady heat, reliable lights, kitchens, medical gear, radios, suits, and rovers. Others sit in the background and make the essentials we cannot ship in bulk forever: food, water, oxygen, and power. Together they form the backbone of a settlement. If any link fails for long, the rest of the chain feels it. The first priority is life support that closes the loop. Closing the loop means recycling air, water, and waste so that losses are tiny and supplies stretch far. It also means using what Mars already offers, a practice called in situ resource utilization, pulling carbon dioxide from the air, melting ice for water, and reusing every drop and every breath. NASA has spent years building and testing these systems. The approaches fall into two broad families. Physicochemical systems use filters, heaters, coolers, and chemical reactions. Bioregenerative systems use living things, plants, and helpful microbes to do part of the work. Physicochemical life support will come first because it is straightforward and predictable. Think of it as an industrial water and air plant shrunk to fit a base. Water from sinks, showers, and even breath and sweat is captured, cleaned, and returned to the tanks. Solid and liquid waste is processed so that water is reclaimed and harmful chemicals are removed. Carbon dioxide exhaled by the crew is scrubbed from the air and converted into forms that are easier to store or vent. Oxygen is made from water using electricity or from carbon dioxide using well-known reactions. These devices use pumps and membranes rather than soil and seeds. They do not need sunlight, do not get sick, and they can be switched on the day the habitat is pressurized. When a part wears out, crews replace it. When a sensor drifts, they calibrate it. This makes physicochemical systems the practical choice for the first missions and the early years. For longer stays, there is a strong case to bring biology into the loop. A bioregenerative system copies what Earth already does. People breathe out carbon dioxide and water vapor. Plants take in carbon dioxide and, with light and nutrients, turn it into oxygen and food. Microbes break down waste into simpler compounds that plants can use. Greenhouses become more than gardens. They are air factories, water polishers, and food producers wrapped into one. Over time, these living systems reduce the mass of supplies that must be launched from Earth. They also add fresh tastes and textures to meals, which helps morale in a place that can feel closed and still. Designing those greenhouses calls for careful control. Inside, temperature, humidity, and carbon dioxide must stay in the right range. Lights must match a healthy day-night rhythm. Nutrients must flow without contamination. Pests must be kept out, and helpful microbes must be kept in balance. Mars's soil, called regolith, is not dirt in the sense we know it. It lacks organics and can carry toxic compounds. So early farms will rely on hydroponics, growing plants in water and nutrient solutions, or on engineered soils made from cleaned regolith mixed with safe ingredients. The goal is stability over drama. Steady harvests of greens, grains, and hardy vegetables that can be counted on. Even then, physico-chemical systems remain in parallel as a safety net. The two families work together, each covering the other's weak spots. None of this runs without energy, and greenhouses may be the hungriest part. They need light for plants, pumps to move water, fans to move air, heaters at night, and coolers on some days. The good news is simple. Mars receives enough sunlight for plants to grow. Near the equator, the daily solar light is in the same broad range as places like Norway on Earth. Forests grow there. With clear skies and well-designed glazing, a greenhouse can gather enough light to keep photosynthesis humming. Mirrors and reflectors can help spread light evenly. Heat captured during the day can be stored in water or rock and released at night to hold temperatures steady. Power for the whole colony asks tougher questions. Early on, there are two main choices: solar or nuclear, or a mix of both. Solar power is familiar and clean. Arrays can be spread across the ground, mounted on tilting frames, and wired into a microgrid. Batteries and other storage systems can carry energy into the night, but Mars is known for dust. A single storm can partly block sunlight for weeks. A global storm can do so for months. Panels can be brushed and blown clean, and robotic wipers or electrostatic shakers can help, yet the light itself still drops during a major event. A settlement that depends only on the sun would have to oversize its arrays and carry heavy storage to ride out the longest storms, and even then margins would be thin. Because of that, many plans include a small nuclear reactor as the backbone for the first base. A compact reactor provides steady power day and night, in clear weather and in storms. It does not care about dust or seasons. Its waste heat can be piped into the habitat to warm living areas and greenhouses, cutting the load on other heaters. Designs tested on Earth favor passive safety, meaning they shut down into a safe state by themselves if something goes wrong. Several small units can be used instead of one big one, so that maintenance can be done without turning the lights off for the whole base. In time, as arrays grow and storage improves, the share from solar can rise, but that early nuclear core keeps life support stable when the sky turns brown. Solar will still do a lot of work. Arrays can be laid out with dust in mind: smooth surfaces, low static charge, and clear access for cleaning robots. Panels can track the sun across the sky. Inverters and controllers can switch between sources without blinking the lights. When storms roll in, the system can shed non-critical loads and give power to air, water, and heat first. The best designs are not flashy. They are forgiving. They let a pump fail without stopping a crop. They let a breaker trip without freezing a room. They give crews time to fix rather than race to save. Energy choices also shape how we make what we need. If power is steady, water can be pumped from ice with heaters and drills that run around the clock. Carbon dioxide can be captured and fed to units that make oxygen for breathing and chemical feedstock for fuel. Waste can be processed slowly and thoroughly to squeeze out every useful molecule. Even simple perks, warm floors, brighter lights during planting, hot showers become possible when the kilowatt hours are there to spare. Looking farther ahead, Mars may offer heat from inside. Geothermal power uses the planet's own warmth, brought up through wells and moved by fluids. On Earth, this works best where the crust is thin or fractured. On Mars, we would need good maps of heat flow and rock structure. Drilling would be hard in a place this remote, but the payoff could be a constant, local source of heat and electricity that does not depend on weather. Even if deep geothermal proves difficult, shallow geothermal using the ground as a thermal battery can help smooth daily swings inside the habitat. Heat can be stored when supply is high and released when demand spikes. Every piece of equipment that supports life ties back to the idea of a closed loop and a steady pulse of energy. Air processors need power to move fans and drive reactions. Water systems need power to run pumps and purifiers. Greenhouses need power to light and feed plants. Kitchens need heat to cook. Clinics need power to sterilize tools. Shops need power for printers and mills that make parts when something breaks. Storage needs power to keep food safe and sensors active. A good plan treats the power system as the quiet heart of the base and gives it more than one artery. As the years pass, the mix will change. Solar will likely expand because it is modular and easy to add in small steps. Batteries will improve. Fuel cells may fill gaps. Nuclear units can be swapped or upgraded. If geothermal steps onto the stage, It can take over baseload duties and let other sources focus on peaks and special jobs. Whatever the mix, the rule stays the same. Critical systems first, then growth. Back at the core of life support, bioregenerative pieces can take on more load as confidence grows. Early crops focus on fast-growing leafy greens, herbs, and a few reliable staples. Later, fruits and grains join the menu. Waste streams become inputs rather than problems. Cardboard, plant stems, and kitchen scraps can be rendered into compost or fed to bioreactors. The air feels better when plants are busy. Water cycles through tanks and trays and comes back cleaner each loop. Crew health benefits from fresh food rich in micronutrients that are hard to ship in perfect condition. Even so, the settlement will keep its physico-chemical backbone. Filters and scrubbers will remain in place to catch what biology misses. Oxygen generators will run to cover nights and storms. Backup stores of food and water will sit, sealed and labeled, always ready. This layering is not overkill. It is how you make a harsh place safe. On Earth, we trust that the air outside is fine and that power plants far away will keep our lights on. On Mars, the base itself must guarantee both. It does so by keeping options open. In the bigger picture, these choices guide what cargo flies first. Life support racks are compact and proven, so they go on the early flights. Greenhouse hardware follows with seeds, nutrient mixes, and tools. Power comes in 2 boxes, a crate of solar arrays and a small nuclear unit. Pumps, pipes, and tanks fill the gaps. A water workshop lands with drills, heaters, and filters to reach and process ice. Over time, these shipments set up a town that can recycle almost everything and make more of what it needs from the local air and ground. When people imagine life on Mars, they often picture the dome. It will be there, glowing softly in the thin daylight. But what keeps it alive will be the quiet plant rooms, the hum of pumps, the fine mist on greenhouse leaves, and the steady tick of meters that say air. Water and power are all within range. That is the measure of a working colony, not drama, but a calm routine where machines and plants do their jobs, where supplies stretch because loops are closed, and where energy keeps flowing no matter what the sky decides to do. Talking to a base on Mars is not like calling a friend in another city. Distance rules the pace. Even at its best, a radio signal takes minutes to cross the gap between the planets. When Mars is close to Earth, the one-way delay can be about 4 minutes. When Mars swings to the far side of the Sun, that delay stretches to around 20 minutes. Sometimes the Sun sits directly between the 2 worlds and blocks radio waves almost completely for days. That means no quick back and forth, no live voice calls that feel natural, and no remote control that depends on instant feedback. Planning has to accept the lag and work with it. The good news is that we already have a basic relay in place. Several Mars orbiters from NASA and ESA carry communications gear. They pass messages between ground teams on Earth and rovers or landers on the surface. These satellites will not last forever. Their fuel runs down and their parts age, but they show the model. Before people go, new orbiters with stronger radios and bigger antennas will launch to take over the load. Over time, Mars will gain a true network in orbit, like a tiny version of the satellites that support navigation and phones on Earth. With enough coverage, even the blackout periods during solar alignment can be eased by routing signals around the Sun, or by buffering data and sending it when the line of sight returns. Life with delay changes how crews and teams interact. A person in a habitat cannot depend on someone on Earth to guide each step. Training grows deeper. Checklists get clearer. Software becomes a steady partner. flagging problems, and walking people through repairs. Messages become richer, with photos, video clips, and notes that answer questions before they are asked, because the next reply is always minutes away. On the surface, local networks link habitats, rovers, drones, and weather stations so that work flows without waiting on Earth. In orbit, relay satellites schedule passes, prioritize urgent traffic, and store data until a path opens. The aim is calm and steady operations that do not notice the long gap most of the time. Before any of this supports a human voice, the path is paved by robots. That is the proven model. Small scouts like Spirit, Opportunity, and Curiosity taught us how to drive, drill, and sample under Martian skies. They mapped rocks and soils, sniffed the air, and sent back the story of ancient lakes and rivers. Future scouts will go where the first bases might stand. They will hunt for shallow ice, measure how dust moves in that region, and test how well radio signals travel across the terrain. Some units will be small, dropped in clusters to watch weather from many points at once. Others will be big, carrying drills, ovens, and small pilot plants to try the first rounds of turning local ice and carbon dioxide into water and oxygen. The next layer brings cargo that prepares the ground for people. Robotic freighters will land equipment, habitat shells, power units, tanks, drills, and spares. They will check themselves, unfold, and start running. A greenhouse frame can be assembled and sealed, then filled with test racks. A water system can melt and filter ice and store it in protected tanks. Air machines can pull in carbon dioxide and split a steady stream of oxygen into bottles. By the time a crew arrives, the basics will be humming. This lowers risk. It also gives the team a chance to learn the quirks of the site. Dust might cling more than models predicted. A slope might channel winds in a certain season. Knowing in advance turns surprises into routine. Many in the field picture the first address on Mars as a research station built by many nations, much like the International Space Station, but set on solid ground. The layout would be modest. A few connected modules, a small greenhouse, a power core, a landing area, and workshops. Scientists and engineers would live and work there for months at a time. They would study rocks and ice, run life support tests, and learn how to keep a small town alive, far from help. The station would be a place of patience, where simple, reliable systems carry more weight than glossy tech, and where international crews share methods and data in the open. NASA's broad plan for reaching that point has been described in 3 phases that build skill step by step. The first phase, called Earth Reliant, has unfolded on the International Space Station. Astronauts have studied how long stays in microgravity change the body, how bones thin, muscles weaken, fluids shift, and vision can blur. Engineers tested how to recycle air and water almost completely. They learned how to keep hardware running for years with careful maintenance. All of this is basic training for any deep space trip. The second phase, called the Proving Ground, moves operations out near the Moon. This region is close enough for quick help if needed, but far enough to test deep space routines. The Orion spacecraft stands at the center of these missions. Orion is the first crew vehicle built by the United States to travel beyond low Earth orbit since Apollo. It pairs a crew module for launch and splashdown with a service module that provides power and engines in space. Early flights test the heat shield, the navigation, the docking systems, and life support without a crew. Then come crewed flights that take people farther from Earth than anyone has gone before. These trips are not about flags or footprints. They are about learning to live and work where help is days away, not minutes. A one-year mission in deep space is planned as a capstone to show that crews can thrive through long cycles without the safety net of constant ground passes and emergency return routes. The third phase, called Earth Independent, aims at the early 2030 seconds for the first crew to reach low Mars orbit. The goal of that pioneer mission is modest on purpose: enter Mars orbit, operate safely, test, transfer and habitat systems, run telerobotic work on the surface, and return to Earth. No surface walk is planned for that first trip. The point is to retire risks and gather data. During the same period, engineers will keep refining the hardest parts of a landing: entry through thin air at high speed, descent under variable winds and dust, and the final seconds when engines guide a heavy craft to the ground. In parallel, robotic missions will continue to scout, and sample return efforts will bring rocks and soils from key sites back to Earth's labs. These samples will be read with tools that cannot fly, and their secrets will steer the choice of landing zones for later crews. Orion's design reflects lessons learned since the 1,960 seconds. It is larger than Apollo's command module, giving a bit more room to move and allowing a slightly bigger crew. It is built to accept multiple destinations. The idea is not to hardwire one mission profile, but to make a vehicle that can go to lunar orbit, deep space points, and eventually to rendezvous with Mars transfer stages. For landing on a world, another component will always be needed: a lander built for that gravity and that air. On the Moon, Apollo could descend with a mostly vacuum-tuned system. On Mars, the lander must handle hypersonic entry heating, supersonic flight, and the complicated shift to rockets for the last stretch. That craft will be a major project in its own right. NASA is not alone in this long arc. The European Space Agency has set goals through its Aurora effort that link robotic and human exploration and keep the search for life at the center. ESA's ExoMars program launched a mission in 2016 and planned follow-on work to drill below the surface, where organics might be protected from radiation. Other nations are in the game. India, Japan, China, and Russia have planned or flown robotic probes to study Mars from orbit and from the ground. Some plans in China and Russia point to human missions in the 2040 to 2060 range. These timelines are long and can shift as budgets and priorities change, but they show a broad interest in turning Mars from a distant light into a place that many agencies know well. Even so, among national programs, NASA has been the most explicit about sending people in the 2030 seconds under the Journey to Mars banner. The three phases: Earth-reliant, proving ground, Earth-independent, lay out a ladder from today's low Earth orbit work to deep space operations, and then to Mars orbit. The schedule has moved as technology and funding move, but the sequence holds. Build the basic skills close to home, prove the hardware and human routines near the Moon, where return is possible within days. Then stretch to Mars orbit and practice running surface robots by hand from above, so that the first crews to land already know the ground they will touch. Communications fit into each phase. On the station, delay is tiny, and crews can talk live to controllers. In lunar space, there is still no big lag, but teams learn to work with brief outages and the need for local autonomy. In Mars orbit, the true delay arrives. Crews there will drive rovers on the surface with near real-time control, a huge improvement over the slow back and forth from Earth. They will also act as a relay for signals, easing the burden on orbiters and letting ground teams focus on science instead of routing. By the time people step down a ladder to red soil, the local network will be thick. Satellites above, towers on the ground, and smart, short-range links that keep gear talking, even when dust makes the sky grey. The early years on the surface will look like a field camp, not a city. A crew will wake to a steady routine. Systems checks come first. Air quality, water levels, power, work blocks follow. Sample runs, instrument care, repairs, and building tasks. Messages from Earth arrive as packets, carrying plans, questions, and news. Replies go out in batches, written with care because each answer is many minutes away from being read. The slow rhythm has its own calm. It pushes teams to think ahead and to write directions that are clear even when no one is there to explain them. Cargo cadence will be just as important as voice cadence. Robotic missions will keep delivering parts and supplies on a set schedule so that the base never dips into its deep reserves. Each shipment will carry tools and spares based on the last month's failures. If a valve design proves weak, the next lander brings a better one. If a filter clogs too quickly, the next box holds replacements and an upgraded frame. This feedback loop between Earth and Mars defines the first decade. Measure, adapt, repeat. It turns a hostile place into a workable one by smoothing rough edges one by one. As these steps unfold, more nations and partners will find places in the chain. Universities will run instruments. Companies will provide parts, landers, or services. International teams will share data networks and standards so that a wrench from one program fits a bolt from another. The model of the International Space Station has many flags. One station will inform how Mars grows, even if the logos on rockets differ. The technology to support this growth is not just hardware. It is also the software and rules that keep people safe. Procedures for long delay emergencies will be written and practiced. A person on Mars who sees a leak must act now, not wait. A crew that notices a power drop must shed loads by habit and then trace the fault with help arriving later by text and video. The culture learns to trust checklists and to question them when reality disagrees, logging every step so that lessons flow both ways across the millions of kilometers. A special place in this plan belongs to sample return. Bringing rocks and soils from key locations back to Earth will let scientists search for subtle signs of ancient life, with instruments too large or delicate to fly. It will also tell engineers exactly what local materials are made of, down to small impurities that could affect 3D, printing, concrete making, or metallurgy on Mars. Knowing the feedstock helps design the factory. This knowledge, combined with maps of ice and weather, sets the stage for the first permanent pads, tanks, and domes. Throughout, the limits of physics set the rules. The speed of light fixes the delay. The sun sometimes blocks the line. The thin air fixes how heat shields, parachutes, and rockets must share the descent. The gravity fixes how heavy a lander can be without new engines. Working with those rules, not against them, is how a plan stays real. That is why the early crewed mission aims only to orbit Mars and return. It is a dress rehearsal at full scale. It lets people live with the communications lag while safe inside a ship. It lets pilots fly near the planet and feel how guidance behaves in that gravity well. It lets controllers test every link of the chain that will later support people on the ground. Other agencies will keep adding pieces. ESA's drills and orbiters, India's and Japan's eyes in Mars orbit, China's and Russia's long-range plans for humans in the 2040 2060 window. Each effort adds data, tools, and experience. The timelines are not promises. They are maps that update as the terrain changes, but together they show a human interest that spans borders and decades. When all of these parts, communications, robots, cargo, crew, fit together, the picture feels less like a stunt and more like a supply line. Signals move through a web overhead, supplies land on time, crews send back science and receive clear instructions and fresh ideas. Rovers scout ahead, drills sip water from ice, greenhouses stretch and thicken. The first research station grows, not by sudden jumps, but by steady steps that look almost dull on purpose. Dull is a sign of safety. It means delays are handled by design, not by luck. In that steady state, delay becomes background noise. A message from Earth is like a letter carried by a ship in older times. It arrives, it's read, and a thoughtful answer follows. Work on the ground does not stop while the ship is at sea. It continues with local skill and local gear. That is the level Mars needs to reach, and the route there is clear. Keep building the network in orbit. Keep sending capable robots. Keep landing cargo that prepares the way. Keep training crews to act with patience and care, and keep learning from every pass and every packet. Beyond national programs, a broader community is already working on the same goal, turning Mars from an idea into a lived place. Non-governmental groups and private companies have stepped into the gap between vision and daily practice. They run field tests, publish designs, and push for policies that keep momentum. Among them, the Mars Society stands out for steady, hands-on work. It supports analog research stations in remote areas of Canada and the United States, where crews live for weeks at a time in Mars-like routines. They practice closed-loop habits, trial rover routes, refine checklists, and learn how small mistakes can grow in an isolated setting. The president of the organization, Robert Zubrin, argues that technology today is already close enough to attempt human settlement sooner than most people expect. His point is simple. If a society could reach the moon less than a decade after a public commitment in the 1,960 seconds, then a focused effort now could carry people to Mars on a similar timescale, provided the plan holds steady. That confidence shows up in the private sector as well. Over the last 2 decades, several companies have pivoted from one-off missions to reusable systems, cheaper launch services, and long-range vehicle concepts. SpaceX is the clearest example. Founded with the explicit long-term aim of enabling a human settlement on Mars, it has set its sights not on a small outpost, but on a community that can stand on its own and grow into a city. The logic is practical. A base that depends on a constant stream of shipments for food, air, and fuel stays fragile. A town that can make most of what it needs, that recycles almost everything, and that can send crews home and bring new crews in on a schedule, becomes durable. Reaching that level requires lowering the price of moving mass between planets. With present costs, even a modest settlement would be out of reach. The approach proposed is a linked set of changes rather than one grand fix. Full reusability aims to turn rockets from single-use towers into flight hardware that launches, lands, and flies again with a routine cadence. Refueling in orbit lets ships leave Earth light and fill their tanks from carrier vehicles once they reach space, which saves money and opens room for cargo that actually builds life on Mars. Producing propellant on Mars by turning local carbon dioxide and water into methane and oxygen closes the loop for return trips and for flights between sites. Choosing that methane-oxygen pair is part of the plan because it fits the chemistry available on the planet and stores well enough for long windows. Supporters point to progress as a sign that these levers can move real numbers. They note that hardware cycles have sped up, launch prices have dropped, and reflight has become a normal sight. They also frame the path in clear terms. First, prove the vehicles. Then, prove the refueling. Then, prove the propellant plant. Only after these steps should a large crewed schedule begin. The target picture is a steady lane of traffic rather than a single triumph. In that lane, cargo flights go first, carrying habitats, power units, tanks, tools, and spare parts. Crewed flights follow when the ground is ready to support them without heroics. SpaceX's public sketches imagine a long horizon. The end state is a self-sustaining population on Mars, measured not in dozens or hundreds, but in hundreds of thousands, and eventually in the range of 1 million. To get there, they outline a simple scale model, about 10,000 flights, with around 100 people per flight, spread over several decades. Travel times in early campaigns might be on the order of a few months, with a goal of cutting the trip to roughly 1 month as propulsion and trajectories improve. Vehicles are drawn with a living area above and a cargo bay below, so that a single launch can carry both people and heavy equipment. Payloads in the concept phase reach hundreds of metric tons per trip, enough to move full habitat modules, power skids, drilling rigs, and life support racks in one go. These numbers are meant to be read as targets rather than guarantees. They describe a goal line that helps engineers decide what to build and in what order. The sequence keeps the near term realistic. Even in the most hopeful view, early windows focus on freight. The first waves would deliver the machines that make a place livable: air processors, water plants, greenhouses, power sources, and the parts needed to keep them running. Landing this gear ahead of time lets teams confirm that ice can be reached, that oxygen can be bottled, that tanks and pipes hold pressure, and that dust control methods work in that region. It also means that when the first crew steps inside, the lights are already on and the air already smells clean. Only after these systems prove dull and steady do crew rotations grow. Zubrin's optimism about timing and SpaceX's timelines both come with a note of caution from within the field. Even with strong leadership and fast development, the margin for error is thin. A single overlooked valve, an unexpected storm, or a missed landing mark can turn a neat plan into a rescue. People who build systems for a living use simple phrases to capture this. You must do everything right, more than once, under real conditions. That is not a warning to stop. It is a reminder to respect the difficulty. The work is possible, but it is not easy. None of that dims the core change of the last 20 years. What used to sound like fiction has moved into the realm of hard engineering and program management. Closed-loop life support has run on orbit for years. Rovers have drilled, driven, and sampled far beyond their planned lives. Entry, descent, and landing through thin air have been mastered for small payloads. Reusable rockets have flown and flown again. The missing pieces, heavy landers, orbital refueling at scale, propellant plants that run for months without a pause are now clear and testable. As each piece clicks into place, the picture sharpens. A colony on Mars is not a guess or a wish. It is a pathway laid out in steps. Private groups add texture around that pathway. Analog stations teach crews to live with delay, to document every fix, and to maintain systems until they feel like extensions of the hand. Non-government organizations host design challenges that produce new suit joints, better dust seals, or greenhouse concepts that use less water. Investors fund small companies that specialize in parts of the stack: radiation-tolerant electronics, high-efficiency pumps, light and strong pressure vessels, and software that watches for faults before they bloom. Each small win fills a gap that might otherwise slow the whole. The idea of a city, not an outpost, also changes how the future is drawn. A city needs schools, clinics, workshops, farms, places to eat, places to rest, and ways to move. It needs waste handled without fuss. It needs water that is safe by default. It needs power that stays on when the weather turns. It needs rules that make it simple to do the right thing every day. Those needs force designs toward resilience and toward parts that can be replaced, repaired, or remade with local tools. In the long run, this makes the settlement stronger. In the short run, it sets clear goals for each cargo flight. Bring what allows people to live well, not just to survive. Travel time matters to how people experience the journey. A 2 to 3 month trip is a long voyage, but within the range that crews already train for. A 1 month trip would reduce life support demands during transit and make round-trip missions easier to schedule. Cutting travel time requires more efficient engines, careful routes, and safe windows. It is not guaranteed, but it is a useful target that pushes the craft toward better performance and pushes planners to trim mass wherever they can without touching safety. The timeline for a first crewed flight varies with progress and policy. Some voices point to a horizon of about a decade from the present for that first crossing, with cargo flights leading the way even sooner. Others suggest a slower pace to retire more risks before people ride. Both views rely on the same groundwork: prove reusability in high-energy missions, prove refueling in orbit, prove entry and landing for heavy payloads, and run life support and power systems on the surface without human hands for months at a stretch. When those tests are real, schedules will move from hopeful to firm. What follows is not a grand ending, but a steady beginning. In the coming decades, if these efforts hold, crews will land, work, and stay through full cycles of Martian seasons. Greenhouses will shift from trials to main supply. Tanks will fill with local oxygen and methane. Workshops will turn raw regolith into parts, panels, and pipes. Children may eventually learn under a sky that is thin and pale, and send messages home that take minutes to arrive. The colony will not look like Earth, but it will feel like home to the people who keep it running. Seen this way, Mars is not the finish line. It is the first durable bridge in a wider network, a place that supports exploration of nearby moons and asteroids, a training ground for deeper missions, and a second address for our species. Non-government groups keep the culture lively and curious. Private companies turn bold goals into hardware that launches and lands. National agencies keep standards high and safety at the center. Together, they make a plan that does not depend on a single launch or a single leader. It depends on a way of working, careful, open, and persistent. The claim that a Mars colony is a feasible reality no longer rests on hope alone. It rests on test articles, flight logs, systems that recycle and repair, and designs that learn from each run. If those habits continue, the next chapter will not surprise us. It will read like the ones before it. Cargo stacked and shipped, vehicles checked and flown again, crews trained and rotated, habitats expanded a room at a time. A city grows when daily life becomes normal. On Mars, normal will be the true measure of success.